surface area. And the other factor is how fast the cooling of the droplets during flight. So the competition between surface tension and cooling rate determines whether you get spherical powders or non-spherical. So, and you can get different types of structures, nanocrystalline, dendritic, amorphous structure in your powders. And also collide happening. But to understand the atomization process, we have to recall basic fluid dynamics things. I will not go over the details, but just as a review, we use common dimensionless things like Weber number, Morton numbers, Reynolds number. They allow us to model the disintegration of liquid into fine droplets. And mostly you study atomization using finite element or boundary element methods to determine the powder size distribution. And you also come up with some empirical or semi-empirical equations to predict the average size of atomized powders in terms of different parameters, viscosity, density, and other constants. In a very simple manner, if you're looking at cooling of droplets during flight in atomization, you can consider two main contributions to cooling from cooling. One is convective heat loss from the surface of the droplet, which is controlled by Newton's law of cooling, the simple equation here. The other contribution is radiative heat transfer. The radiation heat loss from the surface of the droplet, which follows Stephen-Boltzmann law, that depends on the fourth power of temperature. So essentially, when you write heat flux due to convection and heat flux due to radiation, you can write the total heat flux by adding those two quantities. And that total heat flux should equate how much heat is released by the droplet in a time interval dt. So the mass of the droplet times the density, the volume times the density, mass times the specific heat, times the temperature decrease in a time interval dt. That is the heat loss. And all of that should equal the convection plus radiation term. So when you go through the simplification, you get this kind of an integral, which gives you the instantaneous temperature of the droplet as a function of time of flight. And this has to be, of course, integrated numerically. You cannot have a closed form solution to this integral. So as good engineers, we simplify things. And we say that, okay, maybe radiation is not a predominant heat transfer for our droplets. So if I ignore the radiation term and just retain the convective term, then the equation simplifies to a very simple form. And after integration, you get this kind of a formula. Ti is the initial droplet temperature. T sub s is the droplet temperature after a certain time t. Tg is the surrounding gas temperature in the chamber. R is the radius, rho is the density, and C specific heat. So essentially, it says that e to the power negative of this is basically how the temperature changes. So if you want fully solid particles, spherical particles, then you want the droplet to reach its certification temperature and release latent heat during flight, so that once the droplet hits the collection surface, you get solid powders. So this kind of thermal considerations are used to design the thermal processes in atomization. Once powders have been made or manufactured, the next step is to characterize the powders to make sure that you have the right size, right shape, and everything. And sieve analysis is the most common way that powders are classified. And I think we all know about it. We put fine, successively finer sieves at the bottom, coarsest one on the top. We put a certain quantity of powders in the top, vibrate the whole system, and allow the powders to sift through. And then we can plot a histograms of how many grams of powders are retained on each sieve and create a distribution curve like that. So very simple process, but the problem is that if you go below a certain size, then the surface forces between powders are so large that powders cluster together even the vibration. So sieve analysis can go down only to a certain size range in micrometers. You have other methods like electron microscopy or laser diffraction that allows you to get finer uh, sizes of particles. So in laser diffraction, basically the particles of different sizes will scatter or diffract laser light at different angles and different intensities. So from the distribution of intensity, you can actually work back the size distribution of powders. Another very common method for size of powders is sedimentation method. Basically, you allow powders to settle in a liquid of known viscosity and density. So the well-known Stokes equation from fluid mechanics gives you the terminal velocity. Particles are very fine, so they attain terminal velocity very rapidly. The only key forces are the weight of the particle, the buoyancy force, and the viscous drag. So the balance of those forces actually gives you the Stokes velocity. And that is what is used for as a principle for sedimentation method of size analysis. The problem is the powders are extremely fine, so they will take a very long time to settle even a short distance. So instead of using gravity, people use centrifuge to speed up the settling process. So when you centrifuge a suspension, you can actually figure out the size of powders by using this kind of a light source. So incident light, transmitted light, the intensities could be calibrated to give you size range. So different techniques have different sensitivity for size range. Centrifugal sedimentation using optical or X-ray methods can go down to very fine sizes. This is in micrometers, so you're almost approaching colloidal particles or even nanometer sized particles. And as you come down in this table, you can only go to coarser powders. Light microscopy, SEM, those can go to about 0.1 micrometers or so. Sieve analysis can go down to only about 5 micrometers or so. So depending on your needs, one can use different methods to find the size. Once the powders have been sized and once you have mixed them in a right proportion for your needs, the next step is to press the powders in the shape that you want to create. So these are some common methods to press powders in a die. A single action press, where we have just one punch pressing upon the powders. Now, because the pressure is going to change inside the bed, the powders far away from the punch will not densify as much as the powders near the punch. So there is a pressure gradient or density gradient in a single action press. Powders are not uniformly packed. A slightly better method is to use a double action press to press powders from both sides. That gives you more uniform packing, and the least amount of pressure will be at the mid plane here. So those are two methods here. Another way is what is called the floating die mode of compaction, which is shown over here. In the floating die mode of powder compaction, the bottom punch remains stationary and the powders are sitting in the die over here. As the top punch pushes down on the powders, the die also comes down along with this here. So both the punch and the die are descending together. There is no relative motion between the punch and the die. You reduce die wall friction. So that's another way that sometimes powders are pressed using a floating die mode. But remember, these methods are very simple because if you have a variable cross section in your part, then even two punches will not work. For example, for a part like this, we will need 3 different punches, and each punch will have to move by a different amount to get a uniform packing. So things will get complex for depending on part geometry. And later in a few minutes, we will see that we have other methods of compaction, isostatic compaction, which give you more uniform packing. So what is the effect of pressure, powder compaction pressure on and other full density pressure. And these are the experimental graphs for different materials, copper, nickel, moly, and you can see that moly is harder than nickel is harder than iron and copper. So at given pressure, get less in moly than soft materials. That we can make out intuitively also. These are the same kind of data of ceramic powders. Calcium carbonate is very soft powder, aluminum oxide is very hard. These are the Norris numbers, and you can see that harder powders are not compacted as much as softer powders. One other thing to note here is that above a certain pressure, the density no matter how high the pressure, you will always end up with some residual porosity. How do you get rid of that? Go to the sintering process. So environment after powder compaction. So these kind of graphs are important because they allow you to select the right pressure for a given type of powder. What should be the pressure above which there is no benefit. The same behavior is seen for beam strength of the part. If you plot beam strength, press part is a function of pressure. You see this kind of a behavior. Higher the pressure, stronger the part, which makes sense. Porosity will show opposite to density. As pressure increases, the porosity content decreases at high pressure. And again, softer materials like copper will have less porosity at a given pressure as compared to harder powders. Lubrication helps both during pressing the part and during ejection of the part. And you can see the effect of lubrication on ejection pressure in this graph. So we're looking at three different pressures: compaction pressure 207 MPa, 414 megapascal, 828 megapascal for sponge iron. And zinc stearate is the lubricant. So you less. So for transmitting standard pressures used in industry for different materials, and you can see they are typically in a few 10 to a few hundred megapascal range. For very, very high density parts, you may have to go to gigapascal range, almost 1,000 MPa. So this is kind of a graph of pressed density or density of the pressed part as a function of pressure for three materials. If you replot these data in a way, this is what you see. So these kind of graphs, if they are plotted on, you're able to distinguish three different regions of compaction. Low pressure region, slightly higher pressure region where you have a linear increase, and then a plateau region, stage 3. So you can see what is happening in these stages. In stage 1 at low pressure, powders are not really compacted, they're just rearranged, and there is not much change in the density. In the second stage, the pressure increases and powders physically deform or fracture, and pores between the powders decrease. Porosity inside the powder also decreases, so there is an increase in density. And above a very high pressure, we are in stage 3, where there is no increase in density beyond a certain value of pressure. And then you're ready for sintering. So these kind of data show how a part behaves under different pressures. And for actual research work, you can use photoelasticity to see interference fringes. Most people use very imaging and find it also used to determine the stress distribution inside the powder beds. But in very simple fashion, you can actually work out how the pressure will distribute in a single action press. So the whole idea here is to look at a disk of powders that is under compression and write the forces acting on that little disc. So create a free body diagram. The pressure that is applied is changing with distance. The friction at the die wall is pointing upwards. So when you go through the force balance analysis and inside the powders at any distance, you're getting the distance act on the punch. So the punch has pressurized the powders, and this is the location x equals 0, and you're going inside the powders. PA is the punch pressure, the applied pressure. PA e to the power negative 4 mu zx over d. Use the friction coefficient, static friction coefficient. Z is a constant parameter. D is the diameter of the die, and x is the distance. So if you plot the graph of pressure as a function of distance inside the powder, this is what you see, an exponential dk. So what do you think about this behavior? Suppose you have 3 dies, a large diameter die, a medium diameter die, and a small diameter die. You are pressing powders under the same pressure in each case, 200 MPa, for example. In which of these dies will we get most densification? Will the larger diameter die give the most densification at this level, or the small diameter? And the answer would be that the large diameter die will give the maximum compaction. And you can see that also from this equation, because the larger the diameter d, smaller is this ratio, but then e to the power negative of a small number is a large number. So a large diameter die will give you better transmission of pressure as compared to a small diameter die. Lubricating a die makes sense because mu, the static friction coefficient, when you decrease it by lubricating, the pressure is transmitted more effectively. So this equation will also apply to double action systems, because all that you do in double action is that at the mid plane, the graph will mirror image itself. So from this punch up to the mid plane, this is the graph. From the other side, from this punch to the mid plane, the graph will come down like that. The smallest pressure will be at the mid plane. In other words, the pressure gradient, the slope of the pressure distance curve will be 0 at mid plane here. So the same equation will tell you the pressure distribution for both single action and double action systems. And you can do the same kind of analysis for other shapes. So suppose you want to make a pipe or tube like this by powder compaction. So suppose this is the die in which you put powders around this core rod, and then you press the powders to make this kind of a shape. So this is the outer diameter, this is the inner diameter, and wall thickness, the thickness of the wall will be 1/2 the difference of these diameters. So if you go through the analysis, you will get the same kind of exponential form for tubular components also. But you will have wall thickness term coming into picture here. So these kind of simple analysis allow us to capture the effect of parameters like size of the die, distance, friction coefficient, the applied pressure. Once the powders have been pressed in a shape, the next step is sintering them. And for metal powders, sintering needs to be under controlled atmosphere. Mostly argon, nitrogen, or a mixture of argon, hydrogen is used. That means a mixture of a reducing gas and inert gas. Batch type sintering can be used, or continuous sintering process on a conveyor, and the parts go through the hot zone of the furnace. Time is controlled by the speed of the conveyor. And very slow heat up, isothermal zone, and the slow cool down. Sintering is also used in additive manufacturing, especially in process like DMLS, direct metal laser sintering process, where you're creating a very complex part layer by layer. So in this case, in this sketch, we are looking at this part being manufactured by using powder. So the slider will push a layer of powders on this region here, and this laser beam will scan only that portion of the powders that is based on your 3D design of the component. So you're sintering selectively certain range of powders. And this is how you build up layer by layer the actual part. So instead of sintering a bulk part, you sinter the powders in exactly the shape that you want to form. Or as a function of sintering temperatures. Typically, higher temperatures give you faster densification and part densify more. What is the effect of size of powders on densification? For a given sintering temperature, finer powders densify faster. You get better density with fine powders just because fine powders have a higher surface to volume ratio. So there is more sintering possible because of contact regions. And even after a sintering is done, you have parts with a certain amount of porosity. Porosity could be open porosity or closed porosity. When you have open pores, they are usually interconnected and they can be impregnated or infiltrated with another metal. So if you have a stainless steel part with interconnected pores, you can impregnate that part with molten copper. Copper will seep or wick through the pores, and once this solidifies, you get a fully dense part. The problem is closed porosity, that is fully enclosed porosity cannot be eliminated. All you can do is basically forge or point the part to try to seal or minimize the closed porosity. You cannot fill closed pores with any liquid. And during sintering, there are a lot of fundamental material processes taking place. There is no melting taking place during sintering most often. You want solid state diffusion to form necks between powder particles, and those necks form by diffusion and viscoelastic flow in the contact region. So diffusion is promoted in the contact region because of curvature effects, basically the Gibbs-Thompson effect, as you call it. Atoms diffuse towards high curvature regions and deposit there to minimize the free energy of the system. And diffusion can take place through the vapor, along the grain boundaries in the powders, along the surface, or via bulk diffusion. And then you also have actual viscoelastic deformation that will cause neck formation. And the problem is that when you sinter multi-phase parts, then how do you figure out the sintering temperature? Normally, sintering temperature is the one that is based on the largest constituent. So if you have an iron-based material, then you select 2/3 of the melting point of absolute melting point of iron as the sintering temperature. But at those temperatures, some of the lower melting point alloying elements could actually melt. So you may end up with what is called a liquid phase sintering process, which is both good and bad. Liquid phase sintering is good because if you have a small amount of liquid forming, the powders will be more tightly drawn together one another. Because just imagine if you have two glass slides with a thin water film in between the slide, they stick better. So the same thing happens with powders. A small amount of liquid phase will help densify. But the negative side of liquid is that once the part is fully sintered, that liquid, once it solidifies, will give you shrinkage porosity. So normally you want to avoid liquid phase sintering, but sometimes you have no control on that, and you may end up having some little porosity because of shrinkage. Yeah, these are some typical microstructures of different materials. Sintered iron is like silicon carbide. Sometimes nanoscale ceramics are added in the powders to minimize grain growth or grain coarsening during sintering process. And we know that especially for ceramic material, porosity is very harmful. If you have slight amount of porosity, the flexural strength, the 3-point bend test strength, elastic modulus, all those properties decrease because of porosities. Metals are more forgiving than ceramics, so even with some porosity, the part will not lose as much strength as would the ceramic part. So here are some other powder-based manufacturing processes. Cold isostatic compaction, hot isostatic compaction, slip casting, tape casting, powder extrusion, and injection molding. Let us just quickly look at each of those using 1 or 2 slides, and then I'll be done with this topic here. So I don't want to take too much time. So what is cold isostatic compaction? In this process, we don't use a punch. We use oil, machine oil, high viscosity oil, powder inside a rubber mold, and the mold is immersed in a liquid oil tank, and we pressurize the oil. So you have hydrostatic situation. Powders are compacted more uniformly from all sides. And after compaction, you take it out, cut open the rubber mold, and sinter the part. Sometimes you do this process at high temperature. They're called hot isostatic pressing, which means you combine pressing and sintering into a single step. But to do that, you cannot use an oil. Instead of oil as a pressurizing medium, we use argon gas. So inside this pressure chamber, you have the heating elements that will heat up the powders while they are pressed. You cannot use rubber molds that you can use in cold isostatic press. So mostly people use sheet metal molds or flexible ceramic molds, which means you have to have flexible mold filled with the powders, de-air, and weld or seal the mold before you put it in this pressure vessel. So heating and pressing are combined. And this process is good for reactive metals, things like beryllium, zirconium, titanium, anything that will contaminate because of heating in atmosphere. So by combining pressing and sintering, you get higher, better quality parts. So cold isostatic, hot isostatic, those are two other pressing processes. Slip casting. This is mostly used for ceramic parts. Very simple concept. It's more like the process that craftsmen use. So the whole idea here is to use very fine ceramic powders, mix them in a liquid, carrier liquid, add some binders, surfactants, deflocculants, and that slurry is poured in a plaster of Paris mold. So you have to make the plaster mold, which means you may have to have a metal pattern over which you pour water and plaster of Paris mixture, let plaster harden, strip the mold from the pattern, and assemble the plaster mold. And then you pour the ceramic slurry in the plaster mold and let it sit. So the liquid part will be drained. It will be absorbed in the plaster mold, leaving a deposit of the ceramic surface. You can involve the sintering. If you want to do some surface treatment, like apply a glaze coating or something, you can do that. So very simple process. It's used for relatively simple shapes, things like bathroom china or thermal insulators. It's a slow process, time consuming, but it is quite inexpensive, and you can utilize almost 100% of the material because any unused slurry is recycled to make more parts. And plaster molds, they absorb the liquid, but they can be dried up to make more parts. So it's a very material efficient process. The process is slow, but it can be sped up by using either pressure or vacuum or a centrifugal force. But if you use the standard process without pressure or anything, then this is what the kinetics look like. The thickness of the deposit is a function of time in the plaster mold. And the graph is parabolic. Initial deposition is fast, and with time the deposition slows down just because as the deposit builds up, the liquid has to flow through a thicker deposit. So it takes more time for the liquid to be drained. So the process slows down with time. But when you apply pressure, higher pressure, then the drainage rate can be increased. Or you can mount the plaster mold on a rotating platform, allow the centrifugal force to drain out the liquid faster. So people try different things to to speed up the process. And as we can see, slip casting slurries are pseudoplastic, which means the viscosity depends on the shear rate. Just because you have high volume fraction of the solid particles, there is a viscosity depends on the shear rate at which the slurry is deformed. Tape casting. Tape casting is not very versatile in terms of the complexity of shape. It just makes tapes or mats or ribbons of ceramics. But it is very important because it's widely used in microelectronic packaging applications. The ceramic substrates that are used in those applications are made from tape casting. Also, these kind of multi-layer capacitors that you can buy in a store. The capacitors, they have alternating layers of a ceramic and metal, a conductor and insulators. How to make these kind of very thin ceramic plates? If you look at the scale bar, it is 300 micrometers. So this is the ceramic region, which may be about 100 or 150 micrometer across. These shiny regions are metal. They are deposited by PVD, physical vapor deposition, but ceramic tapes, these kind of thin tapes cannot be made by powder compaction. So tape casting is used for that purpose. And the idea is very simple. You make a slurry of ceramic powders with a liquid vehicle and pour that slurry over a plastic film. And plastic film is pulled at a constant rate on this table. You pour the slurry and use a doctor blade or a knife edge to control the thickness of the deposit that's coming out. That deposit will dry up, and then after drying, you can collect that plastic film, slice it, dry it, and sinter it. And that will give you a ceramic tape. So extremely thin tape can be created. Ceramic tapes 0.01 millimeter, hundredth of a millimeter to 1 millimeter thick are made using this process. And the variables are obviously viscosity of the slurry, speed of the film that is here, drying and firing shrinkages, the height of the doctor blade, the edge that is controlling the thickness. So this process is used for making flat ribbon type ceramics that are used in multi-layer capacitor, piezoelectric devices, thick insulators, and also substrates for electronic packaging. I will not go into these details, but obviously you have effect of density, the viscosity of the slurry on thickness as a function of velocity. Those features can be studied in more detail. Another process uses powder extrusion. Very simple process like clay extrusion. If you want to make parts of ceramics with very fine holes, you use extrusion. So this is one extruder in which you put your ceramic powders, the liquid binder inside. Either use a screw to screw that slurry right here, or you can use piston mechanism. I'm sorry. The screw mechanism will give you a continuous process. A piston process will give you batch type process. So depending on what you want, you can use those mechanisms. The whole idea is to be able to create hollow parts. Ceramic sleeves that we use for thermocouples, they are made using this process. Or different kinds of honeycomb structure, ceramic filters. All of those things are made using an extrusion process. One thing here is that the slurry that you use should not be very liquid. It is more viscous, more thick as compared to slip casting and tape casting, because during extrusion, you don't want the liquid to separate from the powders. So the slurry viscosity is higher in this case as compared to some other processes. Injection molding. Mostly injection molding was used for plastics, but it is used also for making metal parts and ceramic parts. So here is the basic idea. You mix the metal powders and some polymer powders in 60-40 ratio. If you're using ceramics, again, the percentage remains the same. 60% volume ceramic powders, 40% is the polymer binder. That mixture serves as the feedstock. And that feedstock is put in the barrel of the injection molding machine. And you heat the mixture until the polymer melts. You go over the glass transition temperature of the polymer. So only the polymer melts in the barrel of the injection molding machine. The powders remain solid. So now you have created liquid polymer with fine powders of ceramic or metal suspended in it. You injection mold it in a water-cooled dye to create a green part. Next, you debind the part, which means you try to remove majority of the polymer binder, not all of it. If you remove 100% polymer, then there is nothing holding the part together. The whole thing will crumble. So mostly you can buy feedstock from vendors, DuPont or Hagedis Corporations and others. They provide you the feedstock for whatever powders you want. And the polymer, those powders, is two-component polymer, a major binder and a minor binder. So during debinding, you remove the major binder and leave the minor binder intact so the part can be held together. People were using thermal debinding earlier, but thermal debinding caused distortion in cracking and everything. So heating, now people use catalytic debinding, which means we use vapors of a catalyst, acidic solution, to leach out, to dissolve the polymer. And after that, you get a very porous part, a so-called brown part. And that brown part is sintered to develop full strength during sintering process. So during the heat up of the debound part, the minor binder will burn out while the powder particles just begin to sinter together. And sintering is complete, you have your fully dense part. So this process basically is similar to die casting or plastics injection molding, but it is used to make ceramic and metal parts, very high quality parts, complex little parts. I am told, I've seen several companies that manufacture parts using this. Most of the parts are no bigger than the size of a golf ball. Small parts, extremely complex with excellent surface finish. So those kind of parts are made using this process. How does this process, metal injection molding, compare with other competing processes in terms of production, annual production, and part complexity? This is how it competes. Investment casting is somewhere here. High part complexity, but not very high production volumes. Conventional powder metallurgy, high production volume, but low complexity. Machining, forging, these are over here. MIM, metal injection molding, are somewhere here. High production volume and high part complexity. So that is another process that is very important in industry. And again, you can go into the rheology of the suspension and see how powder size and shape affect the viscosity, because the injection pressures here will be higher than injection pressure used for just polymer. If you were injection molding polymers, you will have used less pressures. Also, the conductivity of the part is changed because of ceramic or metal powders, so the cooling process have to be considered. So I think I'm not going to go into these details here. If my time is up, then I can stop here and I can address any questions if people have. Or if I finish too early, I can go back and talk more about something. But if it's okay, I stop. It's okay. All right. If any question from the audience, and we have
limiting. If the audience is having any query, they might type their queries in the chat box.
Yeah. We want to make it plastic. You should be able to make one. Yeah, pretty plastic. Defect. Yeah. Which process we can use powder metallurgy or plastic? Depends on the practice. First of all, what alloy